In the last lecture, we saw that one way of overcoming this inherent or seeming tension between x dot equal to u as a way of generating references and the actual robot dynamics was to introduce a layered architecture where you had a planner that planned reference trajectories and a tracker that tracked these reference trajectories. What I want to do today, in today's lecture, is see how do we make this architecture concrete for the particular example of a differential drive wheeled mobile robot. And if you recall, going back in time to Module 2, a differential drive mobile robot has two wheels, and the wheel velocities can be independently controlled. So we have V sub L for the left wheel and V sub R for the right wheel. And if this robot is located at x, y, and in this case it's heading straight up, so this is the angle phi, then we saw that the dynamics for the differential drive mobile robot was given by this expression. We also quickly realized that there was something rather unintuitive about this. It's hard to feel wheel velocities. It's much easier to feel what's happening if you're assuming that you can control the speed of the robot directly and the angular velocity, meaning how quickly you're turning. If you're doing that, you instead get a unicycle model. The differential drive mobile robot dynamics is not the unicycle dynamics, but it's close. And in fact, Module 2, part of the things we did in that module was connecting these two. And we actually derived this expression where the right and the left wheel velocities could be related to V and omega directly, meaning the control signals we produce under the unicycle assumption can be directly mapped onto V sub R and V sub L. And that's nice because V and omega are intuitively clear, while V sub R and V sub L are not. So the way we think about differential drive mobile robots is really in terms of unicycles, and then we make this final transformation onto the actual wheel velocities before we're sending the actuation commands. So that's the model we have to deal with. Well, if we now buy that we can use unicycles, then we really have already seen how to make the unicycle go in a desired direction. So here is the unicycle model again. Well, I would like it to go in the direction phi sub d, or phi desired. Well, we actually saw early on that why not use a PID regulator? Well, if I let the error between the desired angle and the actual angle be given by E, and in particular, if you don't do E, but you use arctan 2 of sine phi desired minus phi, comma, cosine the same thing, then you get something that's between minus pi and pi, and you don't have to worry about the angles being poorly behaved. Well, if you use a PID regulator, then we've seen that this actually allows us to track this reference direction, theta or phi sub d, rather elegantly. And as a recap, this is what the PID regulator looks like. It looks rather hairy, but we also saw how to implement it in a rather direct way. So we know already how to track angles. Well, all we need to do then is add in the speed component. So let's assume that the low-level planner has given us a desired velocity, u, where we've assumed then that x is equal to u. Well, we have actually the unicycle, right? And now this vector is actually the desired direction and magnitude we want to move in. And why not simply set that equal to u? U is the desired velocity. Well, if we do that, then we can start seeing, okay, how do we get desired headings out, and what should our velocity be? Well, it's very simple. If we simply take arctangents of u2 over u1, where u2 is the y component of u and u1 is the x component, then that is the angle. So phi desired we get for free. All that remains to be defined then is the velocity component. But hey, check this out. If I take the unicycle model, and I take x dot squared plus y dot squared, and then I take the square root of this, I get this square root here. Well, that is the square root of v squared cosine squared phi plus sine squared phi. Well, this is one of the well-known trigonometric identities. This is exactly equal to 1. So all I get is square root of v squared, which is v itself. So what I've noticed is that if I'm moving the unicycle around, the magnitude of this vector in the direction I'm going with, well, that's v. Well, but I know what the magnitude is of the u vector. It's just the absolute value or the norm of u. So what this simply means is, you know what? V should be equal to the norm of u. Well, the norm of u is the square root of u1 squared plus u2 squared. So I immediately know not only which direction I would like to go in, but how quickly I should go in that direction. So the way to build the tracker for the unicycle robot is simply to take arctangents of u2 over u1 as the desired heading, and then let omega be, we call it PID of E, where E is phi desired minus phi, and V be the magnitude of the u vector itself. That's good news, because this gives us all we need. As before, we plan using our navigation algorithm. Out of the navigation algorithm comes u1 and u2, the direction in which we would like to move. Well, at the end of the day, the tracker needs to spit out v sub r and v sub l, which is the right and the left wheel velocities for the differential drive mobile robot. And now we know what to put inside the tracker block. Phi desired, the desired heading is the arctangents of u2 over u1. Then we use a PID regulator, for instance, or some other regulator, for regulating the angle. So omega is PID of phi desired minus phi. The velocity is simply the magnitude of the u vector, which we know how to compute now. So this gives us omega and v for the unicycle. And then we take this and map it onto the left and right wheel velocities of the actual robot. So this means that we can actually successfully use this layered architecture for our differential drive mobile robots. And this is the way we did it in the experiments that we saw in the previous module. Now, for the unicycle, there is an even more clever trick that is not involving a layered architecture, but it's letting the unicycle really act like x dot is equal to u. And in the next lecture, we will not use this PID-based tracker, but this clever trick as a way of being even more elegant when handling differential drive mobile robots.